Now we continue to learn Chapter 5, Orthogonality. Okay, in this chapter, we will learn 4 sections. Section 1, the scalar product in Rn. First part, the scalar product in R2 and R3. So the definition for scalar product. Two vectors x and y in Rn may be regarded as n by 1 matrices. Okay? The product x transpose y is called the scalar product of x and y. In particular, if we have x written by x1 till xn and by its components, column vector y written by y1 till yn, a column vector, n-dimensional column vector. Then we have x transpose y equals x1 times y1 plus x2 times y2 plus till plus xn times yn. Okay, so this is a scalar product, or we call it an inner product. So this example, given you x and y are 3-dimensional column vectors, then we know that the scalar product of x and y, x transpose y, just equals this row vector, okay, 3 minus 2, 1 times this column vector. So by the matrix multiplication, you immediately know that the result is 3 times 4 minus 2 times 3 plus 1 times 2 equals 8. Okay. And now we know vectors in R2 and R3 can be represented by directed line segments. So given a vector x in either R2 or R3, its Euclidean length can be defined in terms of a scalar product. So the Euclidean length of x equals x transpose x. So this is a scalar product, power 1 over 2. Okay, so if x belongs to R2, you have this Euclidean length equals square root of x1 power 2 plus x2 power 2. And if x belongs to R3, you know that the length, Euclidean length, just equals square root of x1 power 2 plus x2 power 2 plus x3 power 2. So this is the length, Euclidean length. And next, we consider the angle between the two vectors. It's then defined as the angle theta between these two line segments. Okay. We can measure the distance between the vector x and y by measuring the length of the vector drawing the terminal point of x to the terminal point of y. So we see this figure. We have x here from the origin, and to here, this is the terminal point. Okay. And the vector y also origin from the origin to this point. This is terminal point. And then this vector is y minus x. Okay? And then if you want to measure the distance between x and y, you can just measuring the length, the Euclidean length of this y minus x. Okay? So we have this definition for distance. Let x and y be vectors in either R2 or R3. The distance between x and y is defined to be the number, Euclidean length of x minus y. So example, here if x equals 3, 4 and y equals minus 1, 7, then the distance between x and y is given by, so you first compute y minus x by the vector addition, right? So you know that it is minus 1 minus 3 here, and then 7 minus 4. And then you calculate its length, Euclidean length, equals square root of minus 4 power 2 plus 3 power 2, which equals 5. So this is the distance between x and y. Now we consider this theorem 5.5.1. If x and y are two non-zero vectors in either R2 or R3, and the theta is the angle between them, then we have this scalar product x transpose y equals the length of x times the length of y times the cosine theta. Okay, let's consider its proof. Because we know that y minus x is the edge of the triangle, right? Then we know this length power 2 equals the length of x power 2 plus the length of y power 2 minus 2 times the length of x times length of y times cosine theta. We learned this formula before, I think in high school, right? Then it follows that the length of x times the length of y times cosine theta equals 1 over 2 times the length of x power 2 plus the length of y power 2 minus y minus x is length power 2. And then by just calculation, we can get eventually that this length of x times length of y times cosine theta just equals x transpose y, equal this scalar product. So this scalar product just equals length of x times length of y times the cosine theta, where theta is the angle between x and y. Okay, now we give the definition of direction and the angle. So if x and y are non-zero vectors, then we can specify their directions by forming unit vectors. So given you any vector, you divide it by its length, you will get a unit vector, and we call this unit vector is a direction. See? So if u equals x divided by its length, then u is the direction of x. Okay? And similarly, if you define v equals the vector y divided by its length, then v is called the direction of this vector y. If theta is the angle between x and y, then cosine theta equals x transpose y divided by length of x, length of y. So it just equals u transpose v, where u is the direction of x and v is the direction of y. Okay, so you can know the cosine theta equals this number, and you can calculate theta, the angle between x and y. Okay, see an example. Example 3. Let x defined in this way, 3, 4 vector. Y is minus 1, 7, this vector. Be the vectors in example 2. The directions of these vectors are given by the unit vectors. So you have u just equals 3 divided by its length. This length of x equals 5, so 3 by 5, and the second component is 4 by 5. Similarly, we can compute v, the direction of y, so equals y divided by its length. So its length is the square root of 1 power 2 plus 7 power 2. So it's the square root of 50. So it's 5 square root of 2. So you can have v equals minus 1 divided by 5 square root of 2. So it's this one. And the second component is 7 divided by its length, 5 times the square root of 2. The cosine theta, the cosine of this angle is cosine theta just equals u transpose v, equals the scalar product of the directions of these two vectors. Okay, equal the scalar product of the unit vector along these directions. So it is just 1 over square root of 2. So theta equals pi divided by 4. Now, we give this important definition for orthogonal. The vectors x and y in R2 or R3 are said to be orthogonal if x transpose y equals 0, if the scalar product equals 0. You see this example. The vector 0 is orthogonal to every vectors in R2. And the vectors 3, 2, and minus 4, 6 are orthogonal in R2. Because if you do this inner product, do this scalar product, it's just 3 times minus 4 plus 2 times 6 equals 0. So these two vectors are orthogonal. And the vectors, these three-dimensional vectors, 2, minus 3, 1, and 1, 1, 1, they are also orthogonal in R3, because if you do the scalar product, it equals 2 times 1 plus minus 3 times 1 plus 1 times 1 equals 0. So the two vectors, they are orthogonal.